Hello and welcome to this lecture for my college microbiology course. We're looking at Chapter 2, Chemical Principles, or just basic chemistry. And this will be a three-part lecture series looking at the basics of chemistry. So let's get started. So basic definition of chemistry, the study of interactions between atoms and molecules. And so interactions, what does that mean? So how do atoms bond with each other? That's one example of it. Atoms bonding together to make matter. And we have all different sorts and types of matter as a result of atoms bonding together in a variety of different ways. Now, what is an atom? Smallest unit of matter that enters into chemical reactions. This term, this word, was coined about 2,000 to 2,500 years ago, by a Greek philosopher whose name was Democritus. And he used this word because it means in Greek unable to be cut or unable to be divided any further. And so Democritus came up with this concept of the atom as something that if you could take matter, like say a piece of wood, which is I think an example that he used, and kept breaking that, you broke that piece in half, and then you took a half of that and broke it in half, and then took that piece and broke it in half again, and so on and so on. Eventually you would come to this point where you could no longer break it into a smaller chunk. And so through his philosophizing and his thinking, he came up with the idea that all matter can be broken down and subdivided eventually to a final point called the atom, which, as I said, means unable to be cut. And atoms will interact together to form molecules, and then molecules can join each other and form compounds, and compounds can join and form larger compounds. And so we'll see how that works in this chapter. So what are atoms composed of? You've learned this before so many times. In junior high school and in high school, they're composed of electrons, protons, and neutrons. The electrons are the negatively charged particles, and those are the particles that are floating around in the outer electron cloud around the nucleus of the atom, and the protons and the neutrons can be found within what's called the nucleus of the atom, or the center portion of the atom, which makes up a vast majority of the mass of the atom is found within the nucleus. Almost the entire density and mass. The density is derived from the protons and the neutrons, and almost the entire mass comes from the protons and the neutrons. And then the electrons, like I said, are zipping and zooming out around the protons and the neutrons in what's called the electron cloud. Protons and neutrons have approximately the same mass, and electrons have approximately, they're about at 1/2000, so 1/2000ths the mass of a proton or a neutron. So they're way smaller. They essentially have no mass at all, but they have some kind of mass, I suppose. So we're talking about these particles that have a charge on them, either negative, positively charged protons, or uncharged or neutral particles that we call neutrons. And this is a picture of an atom by what's called a scanning tunneling microscope of silicon atoms. A number of them arranged, and you can see in a very regular repeating pattern of these atoms that are forming the element silicon. So those are the three basic components of it. And then protons are subdivided into further smaller particles as well that we don't need to get into. That's beyond the scope of this discussion. So like I said, protons and neutrons are found in the nucleus, and then we have these electron shells. It's more like a cloud, but the shells are used to help give some type of meaning and order and structure to the atom that is understandable for us. But it's more like a cloud in which the electrons are coming into existence and they're going out of existence, and they're popping and they're disappearing, and there's a lot of theoretical conjecture about the electron and how it's existing and what is it doing and how is it moving. But we know that there have to be negatively charged particles and positively charged particles, and then neutrons, which have no charge but give mass to all matter, contributing along with the proton as well. So these shells have energy levels, and electrons can, quote, jump from one level to another depending on how much energy they receive. The electrons can bond with other atoms as well. They can be shared between atoms, or they can be transferred from one atom to another. And so the electrons are the ones that are involved in chemical reactions and chemical bonds. The protons and the neutrons essentially stay where they are. They stay put in the nucleus, while the electrons are getting moved around, and their location is never really static, continuously moving. And micro students, if you want to click on that video, How Small is the Atom? It's an interesting TED-Ed video. That kind of delves into the smallness of the atom, but yet how dense the nucleus of an atom actually is. It's an extremely dense entity within the nucleus of an atom. Very, very small, obviously, almost infinitesimally small, but has a great amount of density. And so that's what adds to the, or contributes to and makes up the mass and the density of all matter. Comes from the protons and the neutrons. Each chemical element has a different number of protons, and we call that on the periodic table the atomic number. And the atomic number tells us how many protons there are. Now, if the atom is not an ion, meaning it hasn't lost or gained electrons, that atomic number will also tell us the number of electrons too. But like I said, electrons can be transferred and shuffled around between atoms, and so you can't count on the atomic number to always be the number of electrons. So it's a minor technicality, but stick with the atomic number telling us the number of protons. Isotopes are elements, are forms of elements with different numbers of neutrons. So they're the same element, but they exist in kind of different forms, and we call them isotopes. So for example, hydrogen exists in 3 different isotopes. And you can see those: protium on the left, and deuterium and tritium. And the only way they differ is in their number of neutrons. You'll notice protium has no neutrons, deuterium has 1 neutron, and tritium has 2 neutrons. And so that changes a lot of the chemical and in cases of other atoms as well, the physical properties of those atoms. So they're called isotopes. Same element, it's all hydrogen, but it varies in the number of neutrons. And then this is what contributes to the atomic mass. So for example, hydrogen has an atomic mass of 1.008 approximately. That's a rounded off number, but 1.008. Now you'll notice that the atomic mass, if you look at a periodic table, of nearly all of the elements, it's not a whole number. It's a decimal point with a number of digits following that decimal point. So in the example of hydrogen being 1.008, what we have here is what's called a weighted average. That's how the atomic mass is arrived. It's a weighted average of all of the elements' isotopes. So notice I said a weighted average. It's not the straight average. If we had the straight average for hydrogen's isotopes, the atomic mass would be 2. You'd have protium with an atomic mass of 1, deuterium atomic mass 2, and tritium atomic mass 3. Well, we add those together and we get 6. Then we divide 6 by the 3 isotopes, and our answer would be atomic mass 2. But it's not. Hydrogen's atomic mass, like I said, is 1.008. And the reason why is because it's a weighted average. So what does that mean? It means that the average is affected by the percentage of the isotope's abundance. So on Earth, protium by far has a much greater abundance than deuterium or tritium. How do we know that? Well, we can look at the atomic mass and see that it's 1.008. I mean, the atomic mass is nearly 1. It's very close to being the atomic mass of protium, which tells us that nearly all of the isotopes of hydrogen that exist on Earth are going to be protium and not deuterium or tritium. So deuterium and tritium exist, but they're in much, much smaller quantities compared to protium. And so it's a weighted average, and that's how atomic mass is derived. That's where the neutron enters any consideration with the elements, as far as the periodic table goes, is with the atomic mass. So anyway, those are called isotopes. They differ in their number of neutrons. There are 92 naturally occurring elements. If you look at a modern periodic table of the elements, there are 118 elements. 92 of them are naturally occurring, and about 26 are commonly found in living things. And of those 26, probably the most abundant would be, I kind of put it to an acronym using the element symbols. We could say SPONCH. SPONCH. And all those are the chemical symbols for sulfur, phosphorus, oxygen, nitrogen, carbon, and hydrogen. So those 6 elements make up they're the vast majority elements. They're the major elements. That's what I'm trying to say. The major elements in living things would be those 6 elements. And then the other 20, with the 26 that are commonly found, are found in much less quantities than those 6 elements that are making up living things. Electron configurations, so you may have seen these whenever you did any kind of, if you've had a college chemistry course, you covered this more, or junior high or high school chemistry. We cover this again where we're showing the shells. And so shell number 1, the lowest energy level, 2 electrons can occupy the lowest energy level outside of the nucleus. And then the next shell can hold 8, and then the shell after that can hold 8, and so on. Now, as we get out in the shells, those numbers vary when we get to other elements, and we can leave that to the chemists. But for what we're looking at in this very basic instruction on chemistry, those are the basic patterns that you'll see. Shell number 1, 2 electrons can occupy. Shell number 2, 8 electrons. Shell number 3, 8 electrons, and so on. And you'll notice that if they don't have the full number, or what's called the octet, there are open spaces within that shell in which electrons can occupy. And so we'll look at that when we talk about bonding and covalent bonding and ionic bonding. So what they want to do, in other words, what atoms want to do, or what they, quote, desire, is to complete their outermost shell, which gives stability to the atom. And the number of missing or extra electrons in this shell is the atom's combining capacity, or its valence. Now this is a very simplified periodic table. You notice there's a big gap in the middle for the transitional elements. But the ones that are shown here, their numbers at the top, 1, 2, and then skip the transitional elements, and then 3 through 8, those numbers represent their valence number. How many electrons do they have in their outer shell? And on the far left, those elements have 1 electron in their valence shell. Clear over to the elements on column 8. Those elements have 8 electrons in their outer shell. And those ones, by the way, happen to be called, do you remember? Probably you do, I hope. They're the noble gases, and they're called noble because they don't bond with anything else, and so they're considered to be noble because they don't mix with the commoners, so to speak, and so they were called noble gases. That's the name given to them because their shells are full, and so they exist as pure elements, and nothing combines with them. So this is what's called the combining capacity, or the term that's used for how they can combine. The term that's used is an element's valence. A compound contains different kinds of atoms, like water or glucose, the 2 examples I have here, and the forces that are holding the atoms in a compound are called chemical bonds. And so these atoms are held together by these bonds in which there are interactions going on between their electrons. The number of protons and electrons is equal in an atom, and if that's the case, then the atom is neutral. But ions are atoms that have either gained or lost electrons, and we call them cations or anions. So in the classic example of sodium and chlorine, you have sodium losing an electron, becoming a cation, so it's become positively charged because it has 1 more proton than it has electrons. And then chlorine becomes an anion because it picks up the electron from sodium, and now it has 1 more electron than it has protons. And so it becomes a negatively charged ion. Ionic bonds are attractions between ions of opposite charge. So one atom loses an electron, another gains, and so in other words, electrons are transferred. One leaves sodium and is picked up by chlorine. And now both of those atoms have complete shells. They have an octet. So if you notice sodium on the left, it's got 2 electrons in its inner shell, which is full. It has 8 electrons now, and it is a full shell, and that means stability. So that 11th electron has been picked up by chlorine and has filled chlorine's single opening. So chlorine had 17 electrons. It picks up another one, and now it has 18 electrons. And so now its outer shell is full, and so those two bond together ionically, and it's called the sodium chloride molecule, held together by the ionic bond in which the electron from sodium was transferred to chlorine. But another type of bond is a covalent bond, and this is when atoms share one or more pairs of electrons. And notice they're not sharing one or more electrons, they're sharing one or more pairs of electrons. So those two are being shared back and forth, being passed continuously between the two atoms. And it's not the same electron, it's any electron at random. And these covalent bonds are stronger and far more common than ionic in organisms. There is one major exception, and it's within the immune system in the antigen-antibody reactions, where weak ionic bonds play a role in that. And I'll talk more about that when we get to specific immunity and looking at antibodies and antigens and how they bind. Now, there are two types of covalent bonds. They are polar covalent bonds and nonpolar. So remember, covalent bonds is sharing of electrons, but there is some variation in the way that those electrons are shared. If the electrons are shared unequally, in other words, if one atom has a stronger pull on the electrons that are being shared than another atom, we call that a polar covalent bond. If the atoms are sharing the electrons equally and everybody's getting along and everybody's happy and they're playing nicely, we call that a nonpolar covalent bond. So there's no region of charge, and that's what these terms refer to. Polar is referring to a region of charge, and nonpolar is referring to no regions of charge. So as I said with the polar covalent bond, where it's pulling the electrons closer to one atom, that atom will develop a slightly negative charge, while the other atom will develop a slightly positive charge in comparison. So it's not an ionic bond. You don't have where the electrons are being transferred, and there aren't ions, but the regions of charge start to form around these atoms, and we call those polar covalent bonds because these regions of charge form. Whereas with nonpolar, there are no regions of charge. And so therefore we say it's nonpolar, or there's no areas of charge existing. And I'll talk more about that later in this chapter. So a hydrogen bond is I guess you could say, a special type of covalent bond. But a hydrogen atom covalently bonds to an oxygen or a nitrogen atom in another molecule. And the example I'm showing here is water. And I'm going to talk about the polar and nonpolar. I guess I'm talking about it sooner than I realized. But H bonds form because the larger atoms, in this example oxygen, which has more protons, I mean oxygen has 8 protons, hydrogen only has 1. That oxygen atom, because of its large proton charge or force that it has, that oxygen atom will pull the electrons from the H atoms closer to them, making the oxygen slightly negative and the hydrogens slightly or partially positive. Now, as a result of this polar covalent bond that is formed between the oxygen and the hydrogens in a water molecule, individual water molecules now become attracted to each other. The oxygen is slightly negative, the hydrogens are slightly positive, and now they all get attracted to each other, and this bond that forms between them is called the hydrogen bond, which is a very stable bond. It takes a lot, for example, it takes a lot of heat energy to break that bond, so that the water molecules will separate from each other and you get steam, for example. So this hydrogen bond forms as a result of the polar covalent bond that forms between each individual water molecule. And this gives great cohesive properties to water. The water molecules kind of stick to each other. Think about like dropping, uh, taking an eyedropper and putting drops of water on a penny, or filling up a very narrow tube, like a very narrow vase, or in the science world, a test tube with water. And that water, whenever it reaches the lip of the test tube, it doesn't just run over the edge immediately. It beads up and it forms this convex surface. And the reason why that happens is because the water molecules are hydrogen bonding to each other and hanging on to each other until eventually they can't hold on and gravity takes over and pulls them apart. If you were to try to do that with something that was nonpolar, say like rubbing alcohol or something, you wouldn't get that convex dome forming over the lip of the test tube or the vase. Or if you put drops of alcohol on a penny, they don't form this like bubble like water does on top of it. It forms this dome-shaped structure. Alcohol will not do that because its molecules are not attracted to each other, and that's nonpolar. Molecular weight and moles. I'm not going to spend much time on discussing the mole at all, really. I just want to show you how molecular weight is calculated. So I use the example of glucose. And if you look at the formula for glucose, C6H12O6, you have 6 carbons, 12 hydrogens, and 6 oxygens. And in order to calculate molecular weight, you take the number of atoms there are of each element, in this case 6, 12, and 6, and you multiply that number by the element's atomic mass. Now the numbers I used, I rounded them off to the nearest whole number, and that's how I arrived at my numbers. So for example with carbon, you have 6 carbons times the atomic mass of approximately 12. It's like 12.011, but rounded to 12. 6 times 12 is 72 grams. 12 hydrogens, roughly atomic mass of 1. That equals 12 grams. 6 oxygens times its roughly atomic mass of 16, you get 96 grams. Add those 3 numbers together and you get a molecular weight of 180 grams. In other words, 1 mole of glucose has a molecular weight of 180 grams. Now, where would you need this? Calculating it in a chem lab or organic chemistry. In microbiology? No. But I just wanted to show you how molecular weight of molecules and compounds are calculated. And it's rather simple. You just need to know the atomic mass, and you use the subscripts, which are the smaller numbers after the letters there. And you just multiply the two together, and then you add them up. And then these numbers can be used to calculate quantities in, say, an organic chemistry lab. If you needed 6/10 of a mole, you could figure out what 1 mole was and then multiply it by 0.6, and then you'd measure out that many grams. But this is not chemistry, so let's move on. So chemical reactions, we'll get into this topic next, and this is important, and it will be important when we discuss biochemical reactions, especially enzymes. But we'll look at it here just as an introduction here in chemistry. So they involve the making or breaking of bonds between atoms, and a change in chemical energy occurs during a chemical reaction, and that change can either be releasing or taking it in. Endergonic reactions will absorb energy, and that's the prefix endo, that means within, it's taking in. And exergonic reactions release energy. Exo means out, and gonic refers to energy. So if you look at the first one, to get an endergonic reaction to take place, energy from the outside must be supplied and then absorbed into that reactant. And so it's absorbing energy, and so we classify that as an endergonic. With an exergonic reaction, the reactants will split once it reaches what's called the activation energy, and we'll talk about that later, especially when we get to enzymes. And when that activation energy level is reached, the reactants break apart, and when the bonds break, energy gets released. So exergonic reaction. And then the one on the right is showing a catalyzed reaction, which is about enzymes, referring to catalysts, referring to enzymes, and that'll be later. But that's just showing the amount of activation energy can be greatly reduced if a catalyst is used in a reaction. And so the reaction can occur much more easily, and certain specific conditions don't need to be met, like a temperature, for example. So endergonic, absorbing energy, exergonic, releasing energy in order for these reactions to take place. This happens within us all the time. Some reactions within us are endergonic, and some reactions within the human body are exergonic, and other organisms as well. So we'll look at reactions a little more specifically. So a synthesis reaction, it does what its name is. It synthesizes something. So you have two separate atoms, ions, or molecules joining together, and a new molecule has been synthesized. And the term that is related to this is anabolism. So anabolic reactions are synthetic reactions where two smaller constituents are joined together to make a larger product. That's an anabolic reaction where things are built up, like say our body builds up carbohydrates, or say glucagon, for example. It's going to take smaller constituents like glucose and other simple sugars, join them together to make a larger carbohydrate. That's an anabolic reaction. Decomposition is the opposite, where you have a larger molecule that gets split into its smaller constituent parts. It's been decomposed. And the term used there are catabolic reactions, or catabolism is the decomposition of molecules in a cell. So catabolic reactions would take a larger molecule, say a protein, and break it down into its smaller constituent parts, break it down into amino acids. Those are catabolic reactions. And so you take these two together, anabolism and catabolism. You take all of your anabolic reactions and all of your catabolic reactions. And now we have our metabolic reactions, or our metabolism. And meta means in the middle. So you're taking, it's kind of like the average of all of the reactions that happen within us, and that's called metabolism. Exchange reactions are part synthesis, part decomposition. So this classic example of sodium hydroxide combining with hydrochloric acid. They break down, so they decompose, but then they rejoin to make something else, and that's synthesis. So you take sodium hydroxide and hydrochloric acid, they just do a switcheroo, and you get sodium chloride and water. All atoms are accounted for on both sides of the equation. Nothing has been lost. And so the law of conservation of matter has not been violated. It can't be. And so everything is accounted for on both sides of the reaction. Those are called exchange reactions. And our final slide for this part are called reversible reactions. We'll look at these. They can readily go in either direction, and each direction may need special conditions. So you can have A plus B synthesizing a synthesis reaction or an anabolic reaction into making the product AB. But AB can reverse and become A plus B. So the product can be broken down into its reactants and vice versa. And the special conditions, sometimes water is needed, sometimes heat is needed, an enzyme is needed. And so these conditions need to be met in order for the reaction to occur. And those conditions are necessary for it to actually happen, to either be a synthesis reaction or a decomposition reaction. Well, that's it for part one. So I hope this was helpful for you. It's a discussion on chemistry, very basic chemical principles. Stay tuned for part two, and thanks for watching.